right, here comes the new stuff. So when we look at chapter 26, we are going to be introduced to some new ideas, but they're all based on the old stuff. This looks like it's a lot more involved, and in some ways it is, but these particular questions that you're going to see usually have a lot of information already set up for you. For example, imagine this is an FRQ. And there are definite FRQs like on AP exams that look similar to this. The first thing we do is we have a set of data, right? So we have the X coordinates, which is the average temperature. And that's your X coordinates there. Your Y coordinates is the amount of electricity used for each of those particular months. And down at the bottom, we have what we remember as our regression output. And there's a lot of stuff here that you're going to want to write down. I suggest that you go back in your book and look this part of it up. There's a lot of stuff down here that you can talk about. You can kind of look at a couple of these and ignore them. So this whole section in the middle here, we will not be discussing anything like that. So when you see weird stuff like sum of squares, degree of freedom, the mean square, F ratio, this is nothing we're going to talk about. Things that I want to pay attention to. There's going to be a bit of information at the top. That's really important. And then all the parts at the bottom. Now, we're used to this one, which is our y-intercept, and this one, which is our slope. But all of these we haven't ever discussed. And we originally said we'll get back to these at some point, and that time has come. So let me just refresh your memory on what all this means. So a lot of the times you may have this dependent variable defined at the top. So dependent means that's the y variable, right? In this case, they've written the power at the kilowatt hours for the y variable. And then you have the r squared variable here, which also allows me to find r if I want to square root the 0.913 and check my slope to see what the sine of r is, right? So in this case, I would have to do this, but I would also have to recognize that r in this problem is a negative value because we checked the slope to see that. The r squared adjusted, ignore that one. We definitely won't be using that at all, so nope. The S you see here is the standard deviation of the residuals. Sometimes that's written S with a lowercase e at the bottom of it, so keep that in mind. If you look beyond that, you have here degrees of freedom, and notice there's a new formula. Degrees of freedom for this chapter are going to be equal to n minus 2. Last time it was n minus 1, but we now have two variables, x and y, so we have to subtract 1 away from each because of each variable we have. So that's why we have 2 degrees of n minus 2 degrees of freedom. So we have 12 points here, one for every month, and n minus 2 gives me 10 degrees of freedom. I am still using the t distribution to do all of this information. So everything you learned about the t distribution in terms of how to read the t chart and use that information, still valid, is still going to be completely usable in this unit as well. Down towards the bottom, let's just kind of define a few things for a minute. This constant in an equation is your y-intercept, which that value is the y-intercept here. Now, this column is about the standard error of whichever one of these I'm looking at, right? So the top value is the y-intercept. This is going to be your slope. So everything in this list, in this horizontal row, is all about the y-intercept. So that's the y-intercept itself. This is the standard error of the y-intercept. This is the t-score of the y-intercept, and this would be my p-value of the y-intercept. We really aren't ever going to look at the y-intercept. We're really not going to get that far into this, but we will definitely look at all of the information listed for the slope. So this is the name of the x-coordinate, so it's the average temp. The actual slope, which describes the relationship between x and y, is always located here. This is the standard error for the slope, right? The symbol for standard error of the slope, SE. Now, B1 is used as the symbol for slope in a lot of our formulas, so I'm going to keep that B1. This is we'll call this B1 as my slope. Just kind of while we're here, beta, capital beta, stands for the population slope. B1 is the sample slope. Okay, so you'll see those. You won't really work with beta very often, but like we have mu and sigma, we always use parameters to write our null and alternative hypothesis. So that's going to come up when we write our null and alternatives. And I'll get back to that in a minute. The thing we have here, we have standard error for the slope, which is this value. This is your t-score, right? And then this is your p-value. Now, these p-values sometimes will be specific. If they're extremely small, you'll see this less than or equal to, right? So notice the p-value is less than or equal to 0.0001. So it's really small. So in this case, I most definitely would reject the null in this particular problem. But I hope you just caught on to something that I just was given most everything I needed to make a decision about a situation like this. So a lot of the time, you get FRQs that look like this where all the information is really given to you. In fact, let's keep going. We have the actual scatter plot where you have average temperature compared to kilowatt hours, right? So that's important to note what's the variable names here. So we clearly see you have a negative relationship. It's fairly strong, I guess, moderate to strong relationship here. I don't know the R value specifically, but I know R squared is pretty high. So you see the dots are fairly clustered around that. So that looks pretty good. We also have the residuals compared to the predicted kilowatt hours. Now, this is an interesting residual plot. We don't typically do this. They're comparing the Y to the residual. It doesn't really matter how you look at it, but we typically compare X to the residual. But anyway, I'm looking at the residual plot. I can also look at in this case, we're looking at a histogram of the residuals, and then I'm going to use these three graphs to do my assumptions and conditions. So let's talk about what's really changed in Phantom and Panic. And for the most part, you'll be happy that the process and everything we do is going to be very similar. We're going to add in a couple of new things just because it's linear regression. So number one, the big thing in the null and alternative is that we're going to be using the symbol beta instead of mu or p. So the way that you write out your null and alternatives are really going to be the same thing. But when you say beta equals 0, in other words, the slope of the regression line is equal to 0, it means there is no relationship between x and y. Here, I'm saying the slope is positive because they both go up together, or the slope is negative, or that I'm just not sure what the slope is, but it's just not the number you're telling me it is, right? Meaning that if I set it equal to 0, that I'm not sure if the positive or negative relationship exists, but I'm going to tell you that there does exist some sort of relationship. And maybe it's positive, maybe it's negative, I don't know. That's really all the things we are looking at here. Assumptions and conditions, there are a couple of things. There's quite a bit of things here. This is probably the longest set of assumptions and conditions we're going to do. But I guess the silver lining in this is that a lot of times they're going to give you all these graphs. So this becomes really pretty easy. I just have to comment on each of the graphs as they're relevant. I don't necessarily need to draw them or write them out, but I do need to kind of list these out and kind of describe why I know it's true or that it fails. Random and independence and 10%. These are, I'm not going to talk about these because they're exactly the same as you had. Do I have a random sample? Are the points that I have independent of each other? Do I have less than 10% of the population? And that really is only true that I would only need to worry about 10% if I have a relatively small population. Linearity or straight enough condition and the equal variances condition is when I don't want to see any pattern in the residual plot. So I'm going to come back to my residual plot here. I can look at this and I can describe it as, well, I'm looking at the residual plot and I do not see any sort of pattern there. So it will pass linearity. Of course, the equal variances, that's that funnel shaped pattern you have. I definitely don't see that either. So both of these are going to pass because we have no pattern at all in the residual plot. The nearly normal condition can be checked. Here we have a histogram, but I can also do that with a normal probability plot. In this case, we have 12 different units. And they're doing it with the Y values in this case. We normally don't do it with Y. They're doing it with X, or we normally do it with X. But here you can see here, the residual values here do follow a unimodal symmetric type of graph. So it's totally going to pass the nearly normal condition. Those are the main differences you're going to have when you look at just the original null hypothesis and assumptions for the significance test and the confidence interval. Now, if you go down to the question, here it says, is there an evidence of association between average monthly temperature and electrical usage? So we've kind of talked about assumptions, the null hypothesis. The name of the test obviously would be the LinReg T test. Or the good news is there's only one test and there's only one interval for this. The p-value and the t-score, I don't even have to do this in the calculator. The t-score here is negative 10.2. And then my p-value, I don't know exactly what it is, but I'm going to kind of go with what they're telling me. It's less than 0.0001. Of course, my alpha level is probably going to be the traditional one of 5%. So again, I've got everything I need to do right here on the paper. It's just a matter of recognizing that and writing down the relevant information. I don't have enough space here to do the whole significance test, but you get the idea. So this is what we're always doing with the significance test. Is there an evidence of an association between the two? Now, if I were doing this specific test, is there an association? Then my choice up here would be the not equal to alternative, because that's just saying there is an association or there isn't one. The null hypothesis is always there is no association. There's no relationship between X and Y. So in this case, we would clearly go in and reject the null because your p-value is so small compared to your alpha level. We do have evidence of an association between the monthly temperature and electrical usage. That's how you write out your conclusion here. A lot of the time, you'll see it written out as describing the slope. So you could talk about for each additional degree increase in average temperature, we would expect the power usage to go, or as the temperature goes up, the power usage goes down. No. Yeah, that's right. So as the temperature increases, the average temperature goes down. So I guess you're measuring mostly cold temperatures. We produce lots of heat. As it warms up, you use less power in the house. So this is apparently a relatively cold area. If the average temperature in May and June, July and August are just in the 60s and 70s, that would be fantastic. So obviously, once you get to a higher temperature, this is not linear. So, but from the data set we have, this is a linear pattern and it goes down as this temperature goes up, the usage of power goes down. I wonder how high you have to go before it starts going back up, because people would tend to use more air conditioner if that were the case. But for what we have, we're just looking at that. We're not extrapolating, also a good word that you're going to need to know later on. Okay, let's go down and finish this up. Explain association using a 95% confidence interval. Now, couple of things here. Number one, you will definitely have the opportunity in this problem specifically to type in the data sets and use your LinReg T interval, just like normal. Make sure that L1 and L2 are what you're using. And then when you do that, you get the right setup when you do LinReg T interval in the calculator. Now, in addition to that, I don't know that I would take that route here, because I've already got all the information necessary. Now, sometimes you'll get stuff like this, but you won't get this. So this, what I'm about to do, is a requirement. So we're going to take the slope. That's negative 50.9 plus and minus the t-score. Now, we have 10 degrees of freedom. So I need to look up we'll say 95%. We're going to look up that number. All right, so if you look in your T table, you're going to find out that your T star for 95% confidence, actually, sorry, 10 degrees of freedom with 95% confidence is 2.228. So we're going to do 2.228 times the standard error for the slope. Well, the good news is we know exactly what that is. That standard error for the slope is right here. So that's 4.98. So times 4.98. And I'm going to take my calculator. I'm going to add and subtract these numbers, and we're going to write those things down. All right, so if you do that, you get negative 62.0 to negative 39.8. Again, I'm going to write this sentence out using my basic confidence interval little conclusion, but I am going to kind of focus in on the idea that I'm going to be talking about slope. So it should have that slope feeling to it. All right, so here's the conclusion. And you're going to recognize there's a lot of that slope description in here. I'm 95% confident that for each increase, we increase in degrees. For each degree increase, yeah, there we go. For each degree increase, we expect the electric usage to drop by 62 to 39.8 kilowatt hours on average. So keep in mind that when you go to write the conclusion out, think about slope and how can I write that out in context. That's a little tricky. So it might take a little bit of practice. But ultimately, that's the process we're going to be doing for this. A couple of formulas here. The ones that I would 100% become very familiar with would be 1 here and then 2 for here. The standard error for the slope, the one you see right here, to be honest with you, that is a formula we look at, but we rarely ever use that, if ever. We'll get back to that later on if that really is something we'll need to look at. But for these two that are circled or squared or rectangled, however you want to think about it, keep in mind those are super important and you definitely want to know those. Some of those may be on your formula sheet, but I'm not so positive they are. There you go. That's the new stuff. That's LinReg, T-test, and T-interval in a really short, fast summary of that. We'll spend a lot more time going over the details of this, but hopefully that gives you a little bit of an overview of kind of what's coming. The next couple of days, we'll be practicing going over these kinds of things, doing some problems, and kind of just making sure we get comfortable doing all this information.